Hi guys, so this lesson's on catalysts. This is what you should know from year one on catalysts. Have a read, pause the video. And this is what we're going to look at for year two. So there's a lot of stuff here, but actually a lot of it is very quick recall stuff. So have a read. Okay, have a read of the starter, pause the video. Okay, so a catalyst. Catalysts are substances that speed up reactions without being used up by providing an alternative pathway with a lower activation energy. Okay, that answer is worth about 2 marks. Just learn it. Heterogeneous catalysts. Heterogeneous catalysts are in a different phase to the reactants. For example, laser pointer thing. Here is the Haber process. All of these reactants and products are gases. The catalyst is a solid. Same for the contact process. All of these are gases. The catalyst is a solid. So heterogeneous in a different phase. So phase is sort of can be thought of. Things can be in a different phase if they're not mixing together. So let's look at homogeneous catalysts. So homogeneous catalysts are in the same phase. An example is esterification. Here we have a liquid, another liquid, and the catalyst is aqueous. So all of these are able to mix together, hence they're in the same phase. So the H plus ions, which comes from sulfuric acid in this case, is a homogeneous catalyst. Oh, just a side note, as you're probably aware, catalysts are chemically unchanged after the reaction. However, they can be chemically changed during the reaction. They just can get regenerated. Or in the case of heterogeneous catalysts, where generally they don't change at all, they just act as a surface. More on that now. I know where first this. The extension asks you to draw an energy profile for uncatalyzed and catalyzed reaction. If you can see, the uncatalyzed reaction has a much higher activation energy, the catalyzed reaction much lower, by providing an alternative pathway with a lower activation energy. Reminder here that reactions that are in equilibrium, a catalyst will speed up both reactions in the forward and the backward direction and will not affect equilibrium. Okay, so that's what we're looking at. Okay, so heterogeneous catalysts, how do they work? They work like this. We should have talked about this first in year one. It should be revision. So what happens is reactants are adsorbed. Remember, this is not absorbed, adsorbed onto the surface. That means it sits on the surface. Bonds are therefore weakened, brings the particles together closer and can hold them in favorable orientation. They'll then react on the surface and they'll then desorb and leave as the product. So have a look at this graph here and try and work out why do you think the shaded elements, metals, are mainly used as catalysts. So pause the video, try and interpret this graph. Okay, so as you can see, looking at the relative rate, you can see these ones have the higher rate, catalytic rate, and it's due to 2 things. The metals on the left-hand side, they adsorb too strongly, so they hold the particles which hit onto them too strongly so that they can't desorb. So that's not a good catalyst if something can't desorb, whereas the ones to the right, they don't have enough strong adsorption. So a molecule would hit onto that surface and then instantly desorb. So it's these ones in the middle which have that sort of perfect area to be good catalysts. And remember, transition metals are also good catalysts generally because they can exist in variable oxidation states. So this allows them to form those interactions and have molecules or particles adsorbing onto their surface. Okay, so too strong, reactants can't move around surface, products cannot desorb. Such as examples are tungsten. Too weak, reactants not absorb, so the molecules, particles don't attach onto the catalyst, such as silver. So ideally, things like nickel and platinum have the Goldilocks. Okay, so specificity. So it's noted that different catalysts are highly specific. So the reaction that may be good for one catalyst is not necessarily good for the other. The reason this works is explained down here, it's shown down here. So, for example, copper is able to form interactions with oxygen and hydrogen like this, holding it in the right position for, say, that bond there to break. And we could then end up with the alcohol turning into an aldehyde. Whereas aluminium oxide, another solid, it could hold the same molecule, ethanol, in a position like this, so that the CO bond could break and release water. So different catalysts are specific for different reactions. So catalysts can get poisoned. This is when a substance blocks the active site. For example, in the Haber process, we have the iron catalyst, where nitrogen and hydrogen meet on the catalyst. They adsorb and react together. Now, sulfur, if there's sulfur present, the sulfur will adsorb onto the iron catalyst, but it won't desorb. It will block the active site, thus preventing the nitrogen and hydrogen from reacting. The same is the case for lead in a catalytic converter. That's why we want to try and remove these substances before we use these catalysts, because the catalyst gets completely ruined and can be expensive to remove that outer layer. You generally might need to replace the whole catalyst. So we're going to talk now about vanadium oxides. This is specifically mentioned in your spec. Let's just skip this. So it says down here, vanadium oxide can act as a heterogeneous catalyst in the contact process. And down here it says students should be able to explain with the aid of equations how vanadium oxide acts as a catalyst in the contact process. So let's look at those equations. This is a lot of just recall heavy stuff right now. So here we go, vanadium oxide in the contact process. The vanadium oxide is a solid. It's in a different phase. It's in a solid state, whereas the reactants are in a and the products are in a gaseous state. So first, the vanadium oxide reacts with sulfur dioxide, producing vanadium with 4 oxygens. So one of the oxygens has actually gone onto the sulfur. So in this case, this is an example of a catalyst. It is actually changing. But in the next reaction, you can see the V2O4 catalyst reacts with more oxygen and the catalyst is regenerated. So overall, the catalyst is chemically unchanged, although it did change within the reaction. Overall, the reaction is just this. Vanadium oxide hasn't changed. You need to know both these equations here. They're quite common for them to ask, and the overall equation. Okay, next example is a homogeneous catalyst, another one you need to know. So this one here, everything is in the same phase. It means it's mixed together. The catalyst is iron 2+ or iron 3+. You can actually use either one, and you'll see in a sec why. This is the overall reaction. We've got iodide reacting with this S2O8 2- ion. Now, this reaction does occur without the catalyst, but really, really slowly. Can you pause the video and try and think, why would this reaction occur so slowly? So there's an obvious answer, and the answer is that they are both negatively charged ions. So when they come close to each other, the negative charges will repel, and they are unlikely to react together, unless they've got lots of energy. Okay. So what happens is the iron 2+, which is in solution as well, reacts with the S2O8 2-, and the iron 2+ gets oxidized into iron 3+, and the S2O8 2- gets reduced into SO4 2-. This SO4 2-, wait, no, it doesn't. So that SO4 2- is the product. The Fe3+, from this, so the Fe2+ formed the Fe3+, then reacts with the iodide ion, and the iodide ion gets oxidized, into the iodine. Now you can see that this one is called reaction number 1, but actually it doesn't matter. We could actually start with reaction number 2. We could start with iron 3+, getting reduced to iron 2+, or we could start with iron 2+, getting oxidized to iron 3+. So either one works as a catalyst. Again, you need to memorize this whole equation up here and both of these separate equations. Okay, finally, this one here is another homogeneous catalyst. And this time, this is an example of something called a autocatalyzation, an autocatalyst. So here's the overall reaction. Again, this one's a pain to remember. You have to remember the balanced equation. So it's 2 manganetes, it's reacting with H+, and it's these C2O42- ions. So the reaction is catalyzed actually by one of the products. The M2+ is the actual catalyst. So this is called autocatalysis because the product is the catalyst. So the reactions that occur with the catalyst. So this reaction occurs first, making some of the catalyst, or you could provide it. And then the catalyst reacts with the MO4-, making M3+. And then the M3+ reacts with the C2O42-, making the product, carbon dioxide, and regenerating the catalyst, which is also the product. Now, these equations are a right pain to remember. I don't think there's an easier way to do it other than just practice. Okay, so that's it. The next slides are just questions. So pause the video, try the questions, look at the answers. So here's the question, here are the answers. Okay. Try these questions, pause the video. Video, try all of them. And there's the answer for that one. That one. And the answer for that one.